The arrival of Industry 4.0 means production is becoming increasingly automated and digitalized. Although companies often have their own proprietary solutions, they're typically not standardized, so manufacturing continues to take place in independent and unconnected units of various size. 2 Czech and 2 German research institutes have joined forces in the creation of a project for new intelligent, secure, and sophisticated solutions for distributed manufacturing in the Industry 4.0 environment. The collective effort led to the establishment of RECAPE, the Research and Innovation Center on Advanced Industrial Production. RECAPE primarily focuses on developing an entirely new concept of multi-site production in which each machine has a digital twin that reflects its characteristics and communicates with other digital twins. Digital twins aren't used only for individual machines. Entire manufacturing units and other entities involved in production can have them too. This makes it possible to simulate the entire production process and reciprocal communication, thus significantly accelerating production preparation while eliminating the occurrence of errors. Thanks to artificial intelligence, manufacturing units are able to share knowledge with one another, and the system can optimize production and respond quickly to constantly changing environments. Moreover, the combination of virtual reality and augmented reality allows additional virtual devices to be introduced to the production process and tested prior to their physical implementation in shop floor. Likewise, potential new suppliers can enter the process, as well as the customer, who can configure the parameters of the required product and make other changes if necessary, even at the last minute. These are the principles upon which future automated multi-site production networks will be built and upon which they will accelerate the implementation of new manufacturing processes, reduce production costs, and make it easier for companies to enter the market and value chains. Production as a service and shared resources. This is the future of industrial manufacturing.
Good morning, ladies and gentlemen. It's my pleasure and honor to welcome at this webinar Professor Wolfgang Wahlster, who is so kind that he prepared a special presentation for all of us for this webinar, presentation entitled Industrial Artificial Intelligence for Zero-Defect Manufacturing, the Future Decade of Industry 4.0. I'm very glad that Professor Wahlster is today with us, even if it is over video conferencing, because the pandemic situation didn't allow him to come to Prague this time. And as a matter of fact, Professor Wahlster is a well-known scientist. Just to repeat, he is a founder and he served more than 20 years as director of German Center for Artificial Intelligence. Currently, he's in the position of Chief Executive Advisor of DFKI and still continues in defining new strategies, new visions, new ideas for industrial automation of the future. And that's why this presentation will bring again vision for the future, new trends, and we are very glad that we can be with him at this moment. So I would like also to announce that Professor Wolfgang Wahlster is honorary doctor of the Czech Technical University, and yesterday the president of the Engineering Academy of the Czech Republic, Professor Zuna, announced that he was elected as a foreign member of Engineering Academy of the Czech Republic. Congratulations to this, Professor Wahlster, and we are glad that you accepted the nomination and that you would like to cooperate with us not only within the frame of Czech Technical University and CIIRC, but also within the frame and under umbrella of the Engineering Academy of the Czech Republic. So this is a brief invitation, which will be followed by presentation. Everybody is entitled also to put questions using either Slido or the people who are watching YouTube or Facebook can use chat for collecting their questions, and Professor Wahlster will answer them after his presentation. So let's start this webinar.
The demonstrator features various production capabilities due to its modular design. We have included 4 new core elements in our system: a module exchange with automated release, adaptive AI methods based on deep neural networks, a Gaia-X connection, as well as modern scalable system architecture. We intentionally chose a simple product for the manufacturing process. A USB memory stick in the form of a studded brick can be individually configured. The customer can select from various colors available. The brick is mounted as desired at the assembly station. Then it makes its way to the data entry station, where process and customer-related data is stored on it. At the end of the line, the state of the final product is compared to the initial order using AI methods before the USB memory stick is output to the customer. An optional production photo is linked to the quality control data button. This option requires a special module to be available in the system. A notice is displayed on the operator's tablet, and the operator gets instructions that this module must be installed in the plant. The tablet now displays detailed worker assistance that provides step-by-step guidance on how to proceed safely through the plug and produce process. The special positioning elements on the stations and the plant system ensure that it is properly aligned, while electromagnets guarantee stability and occupational safety. Each work step must be manually confirmed before the process can continue. This helps to avoid safety issues. An intelligent new connector was developed especially to meet the requirements of modular and autonomous production systems. In this form, it serves as a model for standardization. Manual approvals lead the worker to a legally compliant plant operation. A certified and documented release is prepared at the end of each module exchange. The implemented security elements provide additional protection against unauthorized access. The newly installed module enables the quality control and the related picture, which is later flashed on the USB memory stick. The customer can also select options that require access to external suppliers. For example, we use the orange-colored studded bricks that can be ordered automatically via the European Gaia-X platform and delivered from the Netherlands. Via the Gaia-X node and connection, the production is triggered and the studded blocks are delivered and integrated into our system. On-site production is also possible, and the customer request can be fulfilled without a problem. Artificial intelligence is implemented throughout the plant. Why is this special? You can work at different levels: in the cloud, in an edge data center, directly on an edge device at the station, or directly on a sensor. Another innovation is the skill-based system architecture. It manifests physical machine capabilities and product resources, as well as the higher-level software services for control, planning, and analysis in the factory environment. The automation pyramid transforms into a distributed network. Increased production flexibility is the result of agile expansion, made possible by the modular design.
Dr. Denner, the CEO of Bosch, clearly stated at the summit that only the combination of physical knowledge and digital data will drive the development of industrial artificial intelligence. This is a great opportunity for Europe. Why? Because, of course, in the Czech Republic and in Germany, we have so many excellent engineers who have all this physical knowledge. And of course, we have to combine this with the AI data-based approach. In the United States, this was also recognized in a new AI program launched by DARPA, which is called Next AI. 3 waves of AI are included here, and the most recent one is not statistical learning, because this is now used and very successfully used, I must say, but they say also it should be combined with contextual reasoning. Because handcrafted knowledge, statistical learning is not enough. The next wave is to combine this with models which are known from physics, for instance, physical constraints. Every mechanical engineer knows a lot about these physical constraints, but also special task models for the workers, process models, and of course our digital twins, which was one of the very successful concepts behind Industrie 4.0. On the other hand, as you see here, the training data are also important. If we have excellent training data, which are annotated correctly and which have a high quality, then in the combination, we can ensure really a very good quality of the sensor interpretation, of the reasoning and learning, and the planning in the factory. So why do we want to combine machine learning and model-based inference? These knowledge-free AI methods, like deep neural networks, which are very successful, and we have to use them for visual analysis, for acoustic analysis, so the low-level sensory function of the brain and the cognitive apparatus of humans. These statistical methods can also be used to control search processes in model-based systems and thus make them much more efficient, or to learn the basic operators for model-based inference and planning procedures. On the other hand, we must use model-based AI methods to combine complete or correct machine learning, because sometimes the machine learning results are wrong and they don't be in conformance with physical knowledge. To make the results of machine learning also plausible or explain these results, also some models are also very important and useful. So we have this pendulum between symbolic and numeric. We have very successful symbolic methods like multi-agent systems in the factory. You just saw this in the video. Use of knowledge graphs, constraint and SAT solvers, I will show in a minute. So many methods. On the other hand, of course, Bayesian networks, probabilistic logics, support vector machines, and reinforcement and deep learning are very important. We just finished a new contract, and this photo was taken in Dresden on 9th of October. And you see Professor Mařík together with 2 people from our Ministry for Research and Technology, Professor Lucas and Seisel, but very important also in this industrial leaders, the leader of the AI group at Volkswagen and the leader of the AI group at Skoda. And we discussed the next wave, how can we work together, and signed a contract. And we will have a new project, and this will be the technical part of my talk, namely AI-based quality management. What does this mean? We want to achieve incremental real-time quality monitoring by a hybrid combination, as I just explained, of statistical machine learning and symbolic models. And we want to generate alarms in the machining or assembly process as soon as we observe wrong actions by human workers or a robot, or a wrong interaction between humans or human and robots, or robot and robot in the factory. So one way to do this is hand tracking. We have now advanced methods for doing this. And if somebody does, for instance, a screwing act at in the factory, we can show this person via the HoloLens that he is doing the correct way or incorrect way. This is a very primitive example of screwing in the wrong direction, but of course we have quite complex results when we go to augmented reality and use in the background such a checking process, whether what is done is correct or incorrect. And if not correct, then we also can show the worker how to do it really correctly, if it was not a fatal error. We installed already such systems, for instance, at Bosch, as I will show in a minute. This idea was already used. I gave various talks about it in China in a production for motorbike motors. And what they do is very simple. They do this hand tracking, and then they do a sequence identification, again with visual tracking. So as soon as they detect that the worker has done something wrong, and this happens quite often if you have the batch size 1 production, where a lot of variants are being produced, then this happens. And you are warned, and before the product is finished, it's immediately recognized and can be repaired on the spot. In DFKI in Saarbrücken, Mr. Knoch, for his PhD thesis, together with Dr. Schwarz, worked also on this idea, but in a little bit more advanced way, because there are various tracking tasks. So it's not only the screwing, but also what kind of, here you see what kind of parts he is using, what screws he is using, what is the torque of the screwdriver, and so on. And this is compared internally to a model. We have a model of what really should be done, and this is a BPMN model and a CMMN model. I think you know these notions to formalize processes in the factory. And in this, for instance, in this task, there are some permutations allowed. And of course, the systems allow, when it is checking the quality, also these permutations, but it uses the model as a constraint based and checks both the hand, the picking, the mounting, even with ultrasonic, and also the body analysis. That means the movement of the worker, and then can on the spot recognize any error immediately. And we learned in our seminar with Volkswagen in Dresden that Volkswagen also does exactly this now in their new factory in Zwickau, because manual inspection is very expensive, is very hard to scale, and it's also error prone. They tried this in many factories, but in the long run, it doesn't work. If you have automated stationary inspection, sometimes it's also very inflexible, because you want to check the product at many steps. So if it's stationary, it's not enough. It must be flexible and mobile. And also it's a little bit expensive. So what they did at the Volkswagen factory in the research already is to have what they call a quality inspector as a robot, which is a mobile robot and can roam around and go to some of the important inspection points. He said that in car production, they have 800 different inspection points, and this robot goes around and checks them by visual inspection. At DFKI, we did cooperation with Volkswagen in Hanover, and Wolfsburg. And there in a factory, we also did this inspection with a mobile robot. And the new thing here was that even in mobile teamwork, the robot can move on the assembly floor. So we installed a mobile robot, and this is shown here with a worker. You see the robot, it's a mobile one with 2 KUKA arms, and you also see that the robot is now entering the moving assembly part. Yeah, so this thing moves. Of course, this was still in the lab, but we did it also in the factory itself. So now it goes on this moving logistic belt, and the robot in parallel does 2 tasks and helps the worker to assemble the transmission bearings of a Volkswagen car. And what is interesting here is, again, from the quality control, is that every action these 2 robotic arms and the human do together is inspected, and by comparing it with the task model, whether this is really correct, using the correct tools, using the correct product components, and doing the right thing. Another very good motivation for a project like AIquama, which means AI-based quality management, is that if you do the quality checking too late in the production chain, of course, it may happen that you do some very expensive steps which are unnecessary because the product quality is already so bad that you can not use this product in the end. So it's really not okay product. For instance, here, Dr. Schwarz from the AI Competence Center of Skoda Auto gave this very good example that there is a plasma coating process. This is against corrosion of the motor. It's the most expensive step in the production line. But if you have a method to predict that a certain individual engine is already in such a bad quality state, then you should not go on and do the expensive plasma treatment. So take this out of the line and finish it. So this is not only time saving and energy saving, but also a lot of costs, and especially the tools which decrease after a while are saved. So this is, I think, a very good another example why the incremental and online quality control by AI is really very important. He showed that it is possible by training a deep learning net to predict what the final quality of the motor will be. And if this quality level is too low, you just stop the plasma treatment before it is beginning and save a lot of time and money. A similar approach we have found recently by Bosch and the University of Minho in Portugal. I'm their mentor, so I advise them to go into this direction. And this is the quality inspection for automatically produced displays for cars. The display manufacturing is a very expensive process. Again, and it's done in a clean room. But sometimes when you glue the parts together, there are problems with the gluing, and bubbles will be seen when you track the emerging product visually. But we also found that the rejection efficiency is very high, 100% actually. Bubble detection is 95%. experiment with the CNNs, that means the convolutional neural networks, also very high, but sometimes unfortunately, there are false positives. So that means the system sees a bubble on the display, but there's actually no bubble. And this is the time where we really need model-based insight, because when you think about it, how can such a bubble emerge? Then optically, you will also recognize that sometimes another object which is on the display cover may look like a bubble. So the system is really false, and the neural network is trained. It sees the shape, but the shape has emerged from another object. And we found by a model what's going on in the factory, that actually small folded fibers of the masks the workers in a clean room are using are sometimes causing this problem. Here you see this. This is such a very small fiber which was expelled from the mask of a worker in the factory, and it's actually not a problem on the display. And this is very bad if this is recognized by the CNN, because then you throw away a display which is worth already in this production stage some 100 euros maybe, and of course we want to avoid this. Another very good example is the use of, again, AI methods for inducing anomalies of rotating aircraft components, again, in a cooperation with the DTX Collab. This was done, and here we see that up to now this was only manually done, and now, as in Volkswagen, we use a mobile robot to do the inspection along the wing and find in a way, again, by neural networks which are trained, problems with the material in this case. So it uses, for instance, ultrasonic, but it uses also the well-known fluorescent penetrant inspection in an incremental way. Let me also point out, and you see, I hope you see the videos from fatal accidents with our windmills in Germany. And this is a problem which sometimes leads really to disasters. You see burning windmills, but also parts flying around and maybe even hurting people because of brake failure. And we did a project at DFKI, Industrie 4.0 group, together with some industrial partners in the windmills. And again, we were able, by combining a semantic empowered model of the wind turbine with neural network statistical data analysis in time series, and using this hybrid analysis to really find the cause of this quality problem at the windmill. So we call it hybrid anomaly explanation. Unfortunately, this is post-hoc, so after the accident, but then we have the evidence, because we have a real model of the problem, which goes back to the manufacturing and then improves the manufacturing process. Let me give a last example where I can show that sometimes the complete model-based approach is also good, because then we have 100% verification. This is a rare case, because in most cases these things are computational too heavy, but For instance, in harness production in the cars, it works. Actually, at DFKI, Jana Köhler has shown that using constraint satisfaction methods make it possible to fully automatically produce such harnesses, which are batch size 1, because many cars, because there are so many variants, have their own harness. In the electrical car, this is very often the case. And this means that we want to do this automatically by a harness making robot. But this problem can only be solved not by humans. It's too complex. They do this by hand, by trial and error, but by automatic constraint solving. And here one sees that sometimes when you formalize this as a constraint problem, which is quite a lot of solving of equations with a SAT solver, but it works. In the end, we have the proof that now we have a solution which is 100% correct. So let me conclude. I think the combination of symbolic and numeric methods for online quality control is extremely important. We need for object recognition, for the motion tracking, the sensor fusion in the factory. We need, of course, the numeric methods mainly based on neural networks. On the other hand, we need digital twin reference models, action interpretation, and plan recognition, which, of course, can only be done in a symbolic way. So I must say, deep machine learning, also we have a hype now, cannot guarantee zero error, but we have to do the combination. And this is the strategy now at Bosch. We saw it also at Skoda, at Bosch, at ZF, at Siemens. So I think we have convinced the industry to go this way. And you saw the quotation from the CEO of Bosch. So finally, I would say industrial AI is the key driver of the next decade of Czech-German collaboration on Industry 4.0. AI-based real-time quality management for achieving zero-defect production is the next successful application of AI in manufacturing after the wide deployment of predictive maintenance and real-time production planning. I think predictive maintenance everybody is using now, but the next wave, as I say here, is the quality management, which is on a very mature level, so that we can now really deploy it in the smart factories. And then, as I said, standardization and certification of explainable, robust, and trustworthy industrial AI solutions are the key to broad acceptance of industrial AI. Certification centers at CIIRC and DFKI are the next important steps. So we can do the certification for industry, and this could be a service which we offer to our industries in the respective countries. And finally, only the combined muscle of deep machine learning and model-based AI using constraint solving, terminological reasoning, and multi-agent systems lead to the next breakthroughs in Industry 4.0. So thank you very much for your attention, and sorry for the small technical problem. I hope you have enjoyed the rest of the presentation. Thank you very much.
Thank you very much, Professor Wahlster. And now it's time for questions and answers, of course. So who is willing to put any kind of question in the room here? Yeah, please, Dr. Kolář.
Thank you, Professor Wahlster, for the great speech. Well, I heard also that Industry 4.0 will be followed by Industry 5.0. And there were also some presentation about that recently, but I agree with you that Industry 4.0 still is a good and viable concept, and we have much to do. I would like to ask you. You mentioned AI and machine learning, and so we need data for learning at beginning. But on the other side, the production batches are smaller and smaller. So I would like to ask you how to work with this issue, and if maybe some physics-based digital twins could be one of the possible way. Thank you.
Yeah, thank you for the very good question. The first part of your remark, Industry 5.0, I think this is really a wrong direction, and it's only a small community proposing this. I think they think we should do something new. But first of all, as I said, it's wrong because this is a revolution in industry, and also when we had introduced electricity, this was not done in 10 years. It was in the factories. So this is, I think, just a marketing approach. And actually, if you look closer, what they propose, and this made me very nervous. They said, what was not done in Industry 4.0 is the human assisted by robots. But this is really completely wrong, as Professor Mařík can testify, because from the beginning in Industry 4.0, in our cooperation between Prague and DFKI, we always had the example of a robot helping a human worker. So this is not new, and it's included in 4.0. So I think I already talked to the officials at the European Union, and I think this is more or less stopped. I mean, everybody can do what he wants in research, but I think it's nonsense to talk right now on 5.0. But your second part of the question is more important, and this is a very good issue, because if we have small batch sizes, you are correct, then how do we get the data? And the answer is very clear, and you gave it partially. We need the digital twin physical models to generate synthetic data for the training, because still we cannot work only with symbolic models. We need, simulated data for this what we call sparse data problem. If we have not enough data, we just generate this data as synthetic data, and we have a large, actually 3 projects running now with industry. And I just was at Bosch 2 weeks ago, and we saw that they are already using it in their industrial environment, that they generate artificial data, but these data are, let's say, correct or are realistic because they are generated by algorithms which are based on physical models. Now you could ask, is this possible or not? And actually it is possible, and it sometimes from a theoretical point of view, it's like a miracle, because one could argue that if you have a model generating the data, then what the machine learns is exactly the model. But this is not true. Actually, it turns out that if you mix these synthetic data with some sparse data, maybe you have only a little bit of realistic data, mix them, then you get quite good results. And so it's working. And I think this is the only way to do this, to generate synthetic training data.
Okay, thank you for your answer.
Thank you. I received one question via Slido. So, the creation of semantics model is often time-consuming. Do you see an effort leading to standardizing ontologies for specific industrial application areas? Question of Pavel Burget. Okay.
Yes, of course. This is I think it's a very important point, because in the past, when, and I said this was the second wave of AI, where all the knowledge was handcrafted and then input to the AI system, this is no longer feasible for, especially in our context of Industry 4.0. So absolutely correct. It's not going back to this era, but you are right that standardized ontologies is one of the big advantages. We have this already for industry, but also in industry, it's not one general ontology, of course, but for instance, in aircraft industry, motor development, also for the production in chemistry, there are such ontologies which are already shared between companies. And in Gaia X, this is a very important goal, that actually we can exchange the ontologies in real time, and also the digital twins. I think this is absolutely necessary. We cannot start from scratch. And as I said, not everything has to be modeled, because many things are done just by machine learning. So this mixture is important. And let me reiterate, the physical laws, which are very important constraints for manufacturing, like Ohm's law, Maxwell's equations, and so on. This is not a lot. This is a basic physics understanding, which every student of mechanical engineering also must have. And this can be input in an interoperable way, and has to be used in every moment of machine learning to reject wrong correlations. This happens very often. If you talk, for instance, to Google, they say that about 80% of what is learned is discarded by the ontology, because the system has learned in a nonsense. It's not a wrong learning algorithm, but what was in the data is more or less a pseudo correlation, but not a causal relationship. And even this, if you interpret this as causal, it is against physical laws. And of course, we cannot allow this.
Thank you. So please, Peter.
I would like to stay close to the second question by Petr Kolář. It was about the lack of data and the possibility to generate some artificial data. I think quite common situation is that we have enough data, but we are lacking the interesting data, especially for the predictive maintenance, the data about failures. That
Yes.
We have a lot of data about normal production, and we are interested in some particular situation. And you show a great example with the windmills, which are usually quite reliable equipment and stuff.
Yes.
But then you want to detect that there's a disaster coming, and
Exactly.
and typically you don't have enough training data for that. And you mentioned the possibility to generate some artificial data, but actually, is there a recommended methodology what to consider and how to actually create the models that can cover the possible problems, how to tackle that? Because it reminds me one concrete task from TPCA, Toyota factory in Kolín. They wanted to make predictive maintenance for an engine that was never broken before, but was so important for the whole factory that they wanted to have something in hands. But we didn't know how to tackle that. If we have no data about the possible problem, it's difficult to predict how it can be damaged. So are there some papers, books about it, how to actually generate artificial data in the most efficient way?
Yes, there are papers, also even from our own institute, DFKI, but I must say they are not so much in the domain of manufacturing. We did this, for instance, for BMW and Mercedes in the connection of with regard to autonomous driving. because also there are a lot of situations where you have no material. Let's suppose a small child is running in front of your car. We browse through all video. We have a contract with YouTube so that we can get all the information on YouTube. And but there was no video showing this accident. Why? For legal reasons and ethical reasons. Of course, nobody will upload such a observation by the camera of the car. So you are completely right. It's very hard. But this example shows also very well that it was not too complicated to have a kind of artificial, with advanced computer graphics, be faked pictures from the car, so that instead of the dog, a small child is running in front of the car. And actually, with these, and we had different models of a child, a big fat child and so on, different ages, and thousands of small video sequences were generated automatically, and actually it worked. The car stopped and braked at the right moment. So also these were not realistic events. It works. So you see, in principle, it's possible. But in the windmill case I showed you, it was a lot of engineering behind it. So we really talked to the engineers of the turbine to have quite a detailed digital twin. And of course, if you have a good digital twin, you can, by reasoning over the digital twin, you can find some pathways. When you follow this, even in a finite state automaton, you find that there are glitches in the model which can be dangerous. So that's the way. But I think your question is is very important, because there is no general way and tip how you can do the best with synthetic data. But I can send you references about the other work where we actually were successful with this method.
Thank you.
Okay, thank you. I cannot see. Yeah, please. So, Mr. Matza.
Thank you for very nice, excellent presentation. I would like to ask, we mentioned some issues hidden in the design part of such systems that you described. I would like to ask for deployment. Where do you personally see the most critical barriers and issues in deployment of such methods in factories? Thank you.
I think the main hurdle still is to convince let's say, people who operate the factory, not so much the CEO of the companies, it's easier, but the plant director, who is the operational director, that everything works well, and he is also sometimes in charge of the quality. If the yield is not good enough, he will be criticized by the management. So, and these people, because they know the traditional way of production, sometimes are a little bit skeptical, because they realize that, of course, when you enter AI methods and such, it has sometimes a little bit of statistical nature, and they want to have fully deterministic systems. I think this is the biggest hurdle, and this means that we must have explainable systems, which even for people who are not, specialists in AI, see the point that the probability of an error in the inspection is extremely low, and that if the system says this component is not good, please repair or please discard it because of the quality is not there, then the system should be able to explain in the words of the factory director what happened. Yeah, and this in many systems is not yet the case. So we are very much working, and I think the same is done here at CIIRC, at your part, to have really systems which are able to explain themselves on a higher level, because it doesn't make sense. Some of my colleagues, also even at DFKI in Kaiserslautern, they found good methods to use, for instance, in neural networks to indicate how the systems came to a conclusion. But this doesn't help the factory director. It's much too detailed. We cannot discuss individual neurons, so to speak, to give an explanation. So it's good to find a bug maybe in the network architecture and for the scientists, but it's no good for the people and the workers in the factory. And this is still research to do. We have some approaches, but this problem is still not solved, I would claim.
Okay. So may I also have a question to you? You mentioned also multi-agent system. There was a strong research in multi-agent system at the Czech Technical University in the past and continues. Do you see some potential for a revival of this technology, because it might be useful to integrate different methods and to provide explanations both to the machines, because robots also should get some explanation, and namely people, because the cooperation depends strongly on transparency of each step which is taken or each decision which is made. So what's your opinion concerning this?
Absolutely. I think you are completely correct. I think without multi-agent systems, the next decade of industrial AI cannot be deployed, because, as you said, it's the interoperability, and from my point of view, it's also the in multi-agent research we had a lot of protocols for the interaction between all these agents, so that you really have protocols which where you can make sure the commitment of the other agent to do something. This was one of the central results, and a lot of work went into this. Interactive contract protocols. And when we have, and we observe this, robots working together with humans, let's say a team of two different robots with different skills and two workers with different skills, then of course, without a multi-agent mechanism, it's very hard to explain, as I said, errors in the interaction, because this is one of the most important errors which occurs in actually manufacturing. We saw this in the plant of Volkswagen and Bosch and so on always. They work together with a robot or with other humans, and there is a misunderstanding, or somebody doesn't deliver what he promised at the right time. And this is exactly modeled in multi-agent. So I completely agree that there will be a revival, and we already did it. Maybe you missed the part in the video. We already have a multi-agent system running as a basis of this demonstrator.
Thank you for this answer. One additional small question. Do you have some platforms or standards for communication under development, or each platform or each multi-agent system is still developed in an ad hoc style?
No, I think this is the platforms are extremely important. We had a lot of platforms which were proposed for the industrial internet, the Internet of Things. Some of them were not commercially very successful. You know, the case from GE, but also I would say even the SAP and the Siemens platforms in the end were commercially maybe not yet successful. And I think it's very important not to start with platforms which are too low, so only platforms for the basic IoT communication, but we have to provide higher level platforms. And I think that's a good idea behind Gaia. Gaia X is on a much higher level, even above the cloud level. Some people talk right now about sky computing over the cloud, so to speak, because intra-cloud connection and interoperability between different platforms. I think this is the way to go in the next few years.
Thank you very much. I have here a question from Facebook. Is the use of transformer neural network models the next step in sequential defect detection? So,
yeah, transformer models are very successful, and therefore, of course, we already use them quite a lot, but it's only special and very good architecture for deep learning. But as I said, deep learning is not enough. So the transformer architecture, of course, we have to use, especially in the visual task, and maybe acoustic analysis also in factories. But as I said, transformer architecture does not guarantee also pseudo-correlations being learned. And so the control by model-based approaches has to be done also for transformer architecture. But I agree, this is right now the best. But these architectures are always, every year we hear about a new invention about architectures, and currently transformer architecture is, I would say, the top priority.
Okay, thank you very much. The last chance for question in the audience. Nothing is on Slido or Facebook. No more questions. Is anybody willing? If not, I think our time is exhausted. Professor Wahlster, dear Wolfgang, thank you very much for your presentation, for answering the questions. And I think we are again a little bit step ahead of the pack, understanding what's the future. So thank you for this presentation and for sharing with us the trend, and namely for trying to involve CIIRC and Czech Republic into the future steps towards the goals of the second wave of Industry 4.0. Thank you very much. We really do appreciate.
Best regards. It was a pleasure, and all the best for CIIRC and RICAIP. I'm pretty sure that together we will shape the future of Industry 4.0. Thank you very much for this very important meeting, and I'm of course also ready to answer some questions online later when the video is watched by other people. Thank you very much.
Thank you,
Have a good
Professor Wahlster. Have a nice day. Thank you.
Have a nice day. Thank you.